So we're looking at section 5.5 here on the substitution rule for indefinite integrals. And I know we're actually just beginning our chapter 5 notes. So we talked about 4.9 and now we're doing 5.5 first. And the reason for that is that the substitution rule is actually so important that we want to integrate it throughout the rest of chapter 5. So it really, we think, should be primary and first in this topic. So in 4.9, the previous section, we looked at some indefinite integrals, and those were also called antiderivatives. And there's a funny graphic here just to kind of talk about the differences between differentiation and integration. So when we differentiate like we did in chapter 3, we're going to start and we're going to figure out which rule we need to apply, whether it's the chain rule, the power rule, the quotient rule, etc. And then we're usually done. If not, we repeat and do another rule. Maybe we need to use 2 rules at once. And then that's it. So differentiation is actually pretty straightforward. Now, integration is not as straightforward. So it's all operations, usually they're inverse operations, a little bit harder. So if you think about multiplication and division, like long division, it's harder to do than multiplication is. The same thing is true like exponential functions versus logarithms. Their inverses are going to be more complicated, and that's the true in integration as well. Differentiation is fairly straightforward. There are rules for it that work every time, but integration is going to be started by trying. So sometimes I try a method. If it works, I'm done. If not, there are so many other different choices that I may need to work with. So integration is going to be the big focus in Calc 2. There's a lot of different techniques that we need to work with to learn integration, but we're going to start here getting some basic integration down and some substitution, which is one of the most powerful elementary techniques right here too. So let's take a look at what substitution is all about here on our next page. All right, so it says, with some luck, we can stumble into integrations. With a bit of technique, we can spot patterns that will help us consistently. So we want to be able to spot some patterns, and specifically, we want to reverse engineer the chain rule to create a very useful rule for integration. Once we had the chain rule for differentiation, we used it almost all the time. Almost everything has a chain rule, has an inner function. And so that's the first thing that we're going to need to be able to undo when we integrate, is undo something that was the chain rule. So if you took a function that was, say, f of g of x, and you found its derivative, we know that its derivative would be f prime of g of x times g prime of x. So what I'm looking for here, if I have something that needs to go backwards from the answer to a chain rule back to the original, it's going to be a product. First of all, I'm going to have a function multiplied by another function, and there's going to be an inside function whose derivative is outside. So I need that specific pattern. So that's what they're saying right here. I want to integrate something that's of the form f of g of x times g prime of x, and it's going to integrate into f's antiderivative. So they called it little f and capital F instead of f prime and regular f. No difference there. What is the key is that I have the inner function and the inner function's derivative. Okay, so those are going to be our keys right here. Now, sometimes having all of those f's and g's is a little complicated for trying to figure out what's going on right here. We are, again, just talking about that inner function and that inner function's derivative, but for convenience, we write the inner function as u, and then we can write it in terms of du, the differential, instead of the derivative in terms of u. And that's the way we're going to want to work with these substitutions. Let's take a look at this one right here. Okay, so I want to integrate the square root of 9 minus x squared times negative 2x dx. And so I can see that there is a product. First of all, there has to be a product. And inside that product, there is a function that has an inner function, and hopefully its derivative is outside part of the product. And so we're going to be a little more explicit in calling this out. And so we're going to rename this. So the inner function we are going to call u. And so our inner function, we notice, is u equals 9 minus x squared, inner. And so instead of writing the derivative du dx, we're going to write the differential for it. So the differential du would be, the derivative of 9 is 0, the derivative of negative x squared is negative 2x. And then remember, the difference between a derivative and a differential is that instead of having the du dx on this side, the dx goes on the other side. Now what we're going to do is replace. So in our original, if we rewrite our original here, integral of the square root of 9 minus x squared times negative 2x dx. Okay, so in that original, we can actually replace the inner function here with u, and we can replace, this is the same color, but we can replace this entire outer product with du. So if I do that substitution, this is the substitution step, that's why it's called U substitution. I turn this into the integral of the square root of u du. Now this should look similar to the antiderivatives that we found in 4.9. It's just a standard antiderivative. I will need to rewrite it as a power function. So I've got u to the 1/2 power du. I have not done the antiderivative yet, but we're getting ready to. And then we can use the power rule for integrals here. If we take the derivative, we pull a power down and we subtract. So we do the reverse for the antiderivatives. We add to the power. So 1/2 plus 1 is 3/2. And then I divide by the new power. And so when I divide by 3/2, that's the same as multiplying by the reciprocal. So I get 2/3. And then we add on our constant, because there could have been an arbitrary constant in the function whose derivative went to 0. We're almost done. We did the derivative. The last thing to do is to go back and substitute, because remember we knew what u was. So we're going to plug in u's value for u, and we'll have our antiderivative. So 2/3 quantity 9 minus x squared to the 3/2 power plus c, and that is the antiderivative of the indefinite integral. Okay. This is the process of u substitution. So I'm going to begin by defining a u and a du, and I need to be able to replace all of the x's so that I get down to something that has just u's. I'm not going to be able to integrate if I have some x's and some u's. I need to have just u's. So let's take a look at a couple more examples, and we'll see how this works out. All right. Here is our procedure for substitution, also called change of variables. So given an indefinite integral of a composite function where I have an inside, I want to first of all identify my inner function, which we're going to call u. It's our g of x function, such that a constant multiple of the derivative, so g of x or du, appears in the integrand. Then I'm going to substitute both u equals g of x and du equals g of x dx into the integral. So we get rid of the dx with the du. Evaluate the new integral with respect to u, and then write back in terms of x by subbing back in for u. There is a disclaimer: not all integrals yield the substitution rule. So there may be other rules that we'll need to get. We focus on most of the additional rules when we get to Calc 2, but hopefully, for the most part, we'll be able to integrate the majority of the ones we want to look at with substitution. We may find some that don't, and we'll just have to pause and push those off until we get some more techniques. Okay, so let's see. If I look at the first function here, I see that I have an inner function. I have an inside of 7x. Anytime I have a function that I would need to use the chain rule to take its derivative, I'm going to need to use u substitution to take its antiderivative. So we're going to start with declaring u equals that inner function 7x. Then du is going to be, the derivative of 7x is 7, so 7 dx is the differential. Now, unlike last time, I don't have a 7 dx. I can't throw du in unless I have a 7 dx. I only have a dx, I don't have a 7 dx. Good news though, because 7 is a constant, I can divide both sides by 7, and then I can solve for dx. Now I know what to replace dx with. So I can replace the 7x with u, and I can replace dx with 1/7 du. So our integral is going to become the integral of e to the, instead of 7x, it's u. And then instead of dx, we're going to have 1/7 du. Okay, now after a little bit of rearranging, we can write this, because 1/7 is a constant multiple, it does not have a variable with it, it's a multiplicative constant. I can actually pull it out in front of the integral. So I have 1/7 integral of e to the u du. And I know how e to the u integrates. It integrates into e to the u. Remember, the derivative of e to the x is e to the x. So I'll have 1/7 e to the u. I've taken the antiderivative of e to the u. I got e to the u plus c. And then our final step is just to go back in and replace our u with 7x. And we'll have our general antiderivative. 1/7 e to the 7x plus c. Now we can always check these, because remember, if we take their derivatives, we should get the initial integrand back out.